Good afternoon. Today in this video we would like to talk about hypothesis. So what is hypothesis? In this chapter, it will we will focus mainly on one and two sample tests of hypothesis. So basically, uh, often the problem confronting most of the scientists or engineer is not so much the estimation of a population parameters, but rather the formation of database decision procedure that can produce a conclusion about some scientific system. For example, a medical researcher may decide on the basis of experimental evidence whether coffee drinking increases the risk of cancer in humans. An engineer might have to decide on the basis of sample data whether there is a difference between the accuracy of two kinds of gauge. Or maybe a sociologist that might wish to collect appropriate data to enable him or her to decide whether a person's blood type and eye color are independent variables. So here, in each of these cases, the scientist or engineer postulates or conjectures something about a system, and in addition, each must make use of experimental data and make a decision based on the data. In each case, the conjecture can be put in the form of statistical hypothesis. The procedures that lead to the acceptance or maybe rejection of a statistical hypothesis such as these comprise a measure of statistical inference. First, we need to define precisely what we mean by statistical hypothesis. So, statistical hypothesis is an assertion or conjecture concerning one or more population. Or in another word, a hypothesis is a claim or maybe assumption about population parameters. Here it could be population mean or population proportion. We have two examples here. First, the population mean. The mean monthly cell phone bill of the city is $42. So which means that average cell phone bill in such area is about $42. But another hypothesis is the proportion. For example, the proportion of adults in the city with cell phones is 0.68, which means we compare between population size and how many adults using cell phones, and we get population proportion is about 0.69. The truth or falsity of a statistical hypothesis is never actually known with absolute certainty unless we examine the entire population. This case, of course, would be impractical in most situations. Instead, we take a random sample from the population of interest and use the data contained in this sample to provide evidence that either support or does not support the hypothesis. Evidence from the sample that is inconsistent with the stated hypothesis leads to rejection of hypothesis. It also should be made clear that this procedure must include an awareness of the probability of a wrong conclusion. For example, suppose that we have a hypothesis postulated by engineer that the fraction defective in a certain process is zero point 0.1, and the experiment is to observe a random sample of the product in question. Suppose that 100 items are tested and 12 items are found defective. It is reasonable to conclude that this evidence does not refute the condition that the binomial parameters of zero point 0.1, and thus it may lead one not to reject the hypothesis. However, it is also does not refute that this value 0.12, which is 12 percent of 100, or perhaps even 0.15. As a result, we must be accustomed to understanding that the rejection of a hypothesis implies that the sample evidence refutes it. If we put it in another way, means rejection means that there is a small probability of obtaining the sample information observed when in fact the hypothesis is true. It is also very important to emphasize that acceptance, or rather failure to reject, does not rule out other possibilities. As a result, the firm conclusion is to establish by the data analyst when a hypothesis is rejected. So the foregoing implies that when the data analyst formalize experimental evidence on the basis of hypothesis testing, here the formal statement of this hypothesis is very important. The structure of hypothesis testing will be formulated with the use of term null hypothesis. This hypothesis refers to any hypothesis we wish to test, and it will be denoted by H0. So this null hypothesis, or H0, is simply by we start to assume that the null hypothesis is always true. It's similar to the notion in a law, which is it's always innocent until it's proven guilty. So the rejection of H0 will lead to the acceptance of an alternative hypothesis. And this alternative hypothesis will be denoted by H1. And here, an understanding of the different roles played by the null hypothesis and the alternative hypothesis will be crucial to ones to understand the rudiments of hypothesis testing. Here, the alternative hypothesis, or H1, usually represents the question to be answered or the theory to be tested, and thus its specification is crucial. The null hypothesis H0 nullifies or opposes H1 and is often the logical complement to H1. So in order to reject or fail to reject the H0, we need to understand how hypothesis testing should be done. So here, by hypothesis testing, there are two conclusions that could be made. First, reject the H0 in favor of H1 because of sufficient evidence in the data. Or maybe we can fail to reject H0 because of insufficient evidence of the data. So we need to remember that the conclusion never involve a formal and literal such as accept H0 or reject H0. The statement of H0 often represents the status quo in opposition to the new idea, conjecture, and so on, stated in H1, while failure to reject H0 represents the proper conclusion. Suppose we have a claim of hypothesis that the population mean age is 50 and we take a random sample, let's say 5 random sample, and after we check, suppose the sample mean age is 20. So what do you think? Should we accept or reject? Is it possible that the mean age of the random sample is 20 if the mean age of the population is 50? If not, we need to reject this null hypothesis of H0. So the reason we rejecting this example of H0, first, it is unlikely that uh, we will get this value for mean sample. That's why we reject this hypothesis of H0. First, we need to define an area where we can reject the mean. This area, we call it level of significance. This the level of significance, we define it as a rejection region of the sampling distribution, and it will be denoted by alpha or level of significance. This value typically are zero point 0.01, zero point 0.05, or even zero point 0.1, and it should be selected by the researcher at the beginning of the research when we work with the data, and this value provide the critical values of the test. There are three known methods in order to define the rejection region using the level of significance. First, this level of significance we divide into two and put it in both ends of the area of the region, and outside that upper or lower value of the region will be rejected region. This method called two-tail test, where we put half of this level of significance in the top and the bottom value, and the other two method is by using upper tail and lower tail test, which we use full value of this level of significance and put it in the top region and the lower region, and upper the over this upper tail region will be rejected. Also in the lower value of the lower region will be rejected region. So there are two types of error when making a decision. Based on the types, we have type 1 error, which is the rejection of the null hypothesis when it is true. So when it is true, the reject a true null hypothesis, we call it type 1 error. And the probability of type 1 error is denoted with Greek letter alpha. And it is also called level of significance. The other type of error is when we fail to reject a false null hypothesis. This non-rejection of the null hypothesis when it is false is called a type 2 error. So in testing any statistical hypothesis, there are four possible situations that determine whether our decision is correct or in error. These four situations are summarized in this table. Please take a look. Here we have first, if the H0 is true, if we accept, then it's correct, no error. If we reject the H0, we call it type 1 error. And if H0 is false, if we did not reject it, if we accept it, is called type 2 error or beta. And if H0 is false and we reject the H0, there will be no error and the value is 1 minus beta. So the probability of committing a type 2 error, or denoted by beta, is impossible to compute unless we have a specific alternative hypothesis. And here there is this relationship between type 1 and type 2 error. Here, one thing for sure, that type 1 and type 2 errors cannot happen at the same time. If type 1 error can only occur if H0 is true, and type 2 error can also happen only if H0 is false. If the type 1 error probability increases, then the type 2 error probability will be decreases, and vice versa. And here are the factors affecting the type 2 error. So the possibility for type 2 error increase when the difference between hypothesized parameter and its value is true is decreasing. Beta increases when alpha increasing. So here we would like to review 10 steps when we are testing a hypothesis. First, always state the null hypothesis or H0. State the alternative hypothesis and then choose the level of significance. Choose the sample size and determine the appropriate statistical technique and the statistic to use. Also, don't forget to find the critical values and determine the rejection regions. Also, collect data and compute the test statistics from the sample results. Don't forget to compare the test statistic to the critical value to determine whether the test statistics falls in the region of rejection. Also, make the statistical decision, which is reject H0 if the test statistics falls in the rejection region, and also express the decision in the context of the problem. So we will do a hypothesis test for the mean. Here we have two conditions where the variance is known and when the variance is unknown. So first we will focus on the known variance, and for known variance the test statistics using these z values. So here we have uh, make a approach how to test this hypothesis. First, we have two-tailed tests for the means for known variance. We need to convert the sample statistic to test statistic with z values. So we need to determine the critical z values for a specified level of significance from a table or computer. And then we make decision rule. If the test statistic falls in the rejection region, we need to reject the H0. Otherwise, we cannot reject the H0. So here we have example. So first, we need to test the claim that the true mean of a TV sets in homes is equal to 3, where we assume the variance equals to zero point 0.8. First, if we follow the steps, we need to state the appropriate null and alternative hypothesis. First, the H0 or null hypothesis will be 3, and the alternative hypothesis will be not equal to 3. This is a two-tailed test. We use two-tailed test. So first, we need to specify the desired level of significance. Suppose that we have uh, level of significance equals to 0.05 chosen for this test, and we need to choose a sample size. Here we choose a size of n equals to 100. So after that we determine the appropriate technique. For known variance, we use the z-test or z values. So after that, we need to set up the critical values. For alpha equals to 0.05, the critical z values equals to 1.96. So and then we collect the data and compute the statistic. Suppose that the sample results are with the sample size of 100. The mean is 2.8 and the variance is already known, which is zero point 0.8. We assume that we know the variance, so the statistic will be this value, -2. So we need to plot the graph here. So as we remember, the z value is plus and minus 1.96, and the statistic from the equation we find -2. So should we reject or do not reject this statistics? Here we get the z values is -2, which is smaller than -1.96. So based on the statistics, because it's located in the rejection region, we need to reject or accept this value. So since the value of z is equal to -2, which is lower, so smaller than minus 1.96, well, like it or not, we need to reject the null hypothesis and conclude that there is sufficient evidence that the mean number of TVs in US home is not equal to 3. So in testing hypothesis in which the test statistic is discrete, the critical region may be chosen arbitrarily and its size determined. So if alpha is too large, it can be reduced by making an adjustment in the critical value. It may be necessary to increase the sample size to offset the decrease that occurs automatically in the power of the test. In p-value approach testing, here the probability of obtaining a test statistics is more extreme, which we will use equal or larger or equal or smaller than the observed sample value, given that h0 is true. This is also called observed level of significance, where the smallest of alpha for which h0 can be rejected. So this p-value approach testing is simply convert the sample statistic to test statistic, for example z statistic, and then we calculate the p-value from a table using or a computer, and then compare this calculated p-value with alpha. If p-value is smaller than alpha, we may reject the h0. If a p-value is larger or equals to alpha, we cannot reject the h0. So simply p-value is the smaller number of the level of significance. And how is it these p-values differ from classic hypothesis testing? It is tempting at this point to summarize the procedure associated with testing. However, some freshmen of student usually should understand that there are differences in approach and philosophy between the classic fixed alpha approach, that is climaxed with either a reject or do not reject h0 conclusion, and the p-value approach. In the latter, no fixed alpha is determined and conclusions are drawn on the basis of the size of the p-value in harmony with the subjective judgment of the engineer or scientist. While if we are using a modern computer software, we'll output p-values. Nevertheless, it is important that we understand both approaches in order to appreciate the totality of the concept. Then, thus, we offer a brief list of procedural steps for both classical and the p-values approach. First, approach to hypothesis testing with fixed probability. We need to state the null and alternative hypothesis, choose fixed significance, choose appropriate test statistic, and establish a critical region, and reject HO if the computed test statistic is in the critical region. Otherwise, no rejection. And also we need to draw a scientific or engineering conclusion. Let's see for another p-value example. So here, how likely is it to see a sample mean of 2.04 or something further than the mean in either direction if the true mean is 3.0? So 2.84 will be translated to a z-score of z2 minus 2.0, where p-value for z less than minus 2 is equal to 0.0228, where p-value of z larger than 2 is equal to 0.0228. So the p-value will be 0.0228 plus 0.0228 which will be 0.456. So after that, we need to compare the p-value with the alpha value. If the p-value is less than alpha, we need to reject this H0. Or if the p-value is larger or equal to alpha, we cannot reject the H0. So here we have the p-value equals to 0.0456 and the alpha equals to 0.05. Since the p-value is less than the alpha, we may reject the null hypothesis. So what is the connection to the confidence intervals? So 4 mean equals to 2.84 and variance of zero point 0.8 and n equals to 100. The 95% confidence interval will be between 2.6832 until 2.9968, and since this interval does not contain the hypothesized mean, we may reject the null hypothesis at alpha equals to 0.05. So as I mentioned earlier, if we have two-tailed test, which is alpha divided by 2 and put it in the both ends, lower and upper ends, we have two cutoff values or critical values, and this will define the rejection region of this test. If we have one tail test, the lower tail test and the upper tail test, and these both one tail tests only have one critical value since the rejection area is only at one tail, which is upper or lower tail. Here the configuration for lower tail test, we only reject if the value is lower, and for upper tail test, we only reject if the value is higher. Another example for upper tail test for known variance. Here, a phone industry manager thinks that the customer monthly cell phone bill have increased and now averaged over $52 per month. So the company wishes to test the claim, and here we assume, because the variance is known, we assume the variance is equal to 10. First, we need to form the hypothesis test. We need to define the H0 and also H1. And H0, we need to, in this case, we use the monthly average is not over $52 per month, and the alternative hypothesis is larger or greater than $52 per month, and we need sufficient evidence to support these manager claims. Now, since we are using the upper tail test, we need to define the rejection region, which is in the upper values of the working area. And here, with the alpha is 0.10 is chosen for this test, we need to define the rejection region, which is over 1.28, and if the z values is larger than 1.28, we will reject the null hypothesis. So based on the calculation, of this using these critical values, we may put it in table like this. So according to the table, the value still inside or below the critical values of 1.28, so we cannot reject the null hypothesis for this case. So another example for test statistic. So since the population size is 100 and we cannot get all the 100, we need to take just statistic sample, which is equals to n equals to 64. With this value, with a mean of 53.1, and we still remember the variance is equal to 10, it already assumed. So the test statistic is this value 0.88, and based on this example decision, we reach a decision and interpret the result where the z values equals to 0.88 is lower than 1.28, so we cannot reject the h0 since z values equals to 0.88, which is lower than 1.28. There is no sufficient evidence that the mean bill is over $52. If we use the p-value solution, we need to calculate the p-value and compare it to alpha. Assuming that the mean is 52, we may calculate it and get the p-value where the z-value is equal to 0.88, the p-value equals to 0.180 1.1894. So since the value of 0.8904 is larger than the alpha, which is equals to zero point 0.1, we also cannot reject the H0 or null hypothesis since the value of p-value is larger than the alpha value. Now, if we have unknown variance, what should we do? First, we have example of two-tailed test for unknown variance. So as usual, we have this case and we have these values. Now we have to decide the null hypothesis with these values. So here's the solution. We need to draw into a graph and divide the alpha. Since this one is two-tailed test, we put this half value, upper and lower values. So since the variance is unknown, we need to use t-statistics. T-statistic used when we don't know the variance. The critical value is equal to t24 equals to plus minus 2.0639, and based on the t value here, where the value equals to 1.46, and it's still inside the accepted region, not rejection regions, so we cannot reject the null hypothesis because no sufficient evidence that true mean cost is different than $168. Please don't forget to always check the exercise for this first part of hypothesis. The second part of hypothesis will be given next week. And don't forget to upload this exercise at a mass at the given schedule. Don't forget, the schedule will be 1 week from now. Okay, thank you very much for your kind attention. See you in the next video.